So I've turned on the recording. Welcome everyone to yet another Q&A session for COS 217. This is Wednesday, February 17th, which is one day earlier than Thursday, February 18th, which is the due date of assignment 1. So hopefully you have mostly completed it. If you haven't started, good luck on that. So definitely a good idea in general on these programming assignments to do start early, leave plenty of time for the unexpected hiccups, and try to make steady progress on the assignments throughout the usually week and a half to 2 weeks that you have to complete them. So lecture topic for today was pointers and arrays. And I am happy to take questions on any topics relating to those. In general, pointers and arrays are going to be the main focus of assignment number 2. And they are one of the primary ways that we deal with data structures in C. So whenever we're talking about strings, whenever we are talking about linked lists or trees or things like that, we are going to be dealing explicitly with pointers. And so it's important to get into the mindset of keeping track of what are pointers, where do they point at any given point in time, and how do you manipulate them. So questions?
Yes, I had some questions about pages 5 and 6 of the slides.
Okay.
More specifically, they were examples of pointers, and they had a bunch of printf statements, like testing equality. So, yeah, so the first question was on slide 5. I was wondering if you could explain the last two. So the one that starts with star meta equals bacon.
Okay, let me go ahead and share that window. And maybe we can just go through all of them. And do you see the slides in the window?
Yes.
Great, great. So let us kind of go through what's going on here and really try to understand all of these different pointers and where they're pointing, right? So we start by creating 2 int variables. So think of those as just locations in memory that store values. In this case, the values happen to be 42 in both cases. And then we create some pointers. Atoms and bkn are pointers to int. So this syntax basically says that you are declaring a variable. The type is pointer to int. Sometimes you will group the star with the int. Sometimes you will group the star with the variable name. That's kind of a stylistic preference. So we're creating a pointer variable that points to life. We're creating another pointer variable that points to Jackie. And then we're creating a pointer to a pointer, which is perfectly fine. You can also have a pointer to a pointer to a pointer, and so on and so forth. So all of these are perfectly valid types in C. And so here we're creating a pointer to an int and initializing it to point to the pointer. In other words, meta is pointing to atoms in this case. So here, a lot of these printfs and a lot of these equalities here are basically testing how you think about comparing pointers versus comparing what is pointed to by the pointer. And basically, whenever you see a star, that means you're dereferencing the pointer. You're following the pointer and seeing what's there. So if we're comparing, doing this first comparison, we are comparing 2 pointers, and obviously the pointers are pointing to different things, and so we get an output of 0, effectively false, because the pointers are pointing to a different thing. Here we're dereferencing the pointers, so we're asking, are the things pointed to by the pointers equal? And in each of these cases, the pointers are pointing to ints, and the ints happen to have the same value, and so when we dereference these pointers, the values, the ints being pointed to are equal, so we get a 1. So now here, let's start getting a little more complicated. So meta is a pointer to an int. And here we're taking the address of atoms. So unsurprisingly, we initialized meta to be the address of atoms. And so later on, when we compare meta to the address of atoms, we haven't changed anything. So those two are equal. We get a true. Here, we're comparing meta to the address of something different, right? We're comparing meta, which is a pointer to atoms, to the address of BKN. And so, unsurprisingly, those are not equal to each other. And so now we start following pointers. First, we follow the meta pointer. Meta points to atoms. So when we follow meta, we get atoms. We compare atoms to atoms, and we get true. Those two are, in fact, equal. Now, we follow meta. We know that meta points to atoms. So when we follow meta, we get atoms. And we're comparing atoms to broken. Or bacon, I don't know. What was this intended to be?
Brooklyn. It's a Jackie Robinson reference.
Brooklyn, sorry.
So the meaning of life was 42 and Jackie Robinson's number was 42.
Got it. So we're comparing we're comparing what is pointed to by meta, namely atoms, to Brooklyn. Brooklyn is not atoms, so we get a false. Now, we start dereferencing pointers multiple times. So here we have meta. We follow meta. That is this first star. So we follow this arrow, and we get to atoms. We follow whatever arrow is in atoms. That's this second star. So we're actually dereferencing a pointer to an int twice. And so we get an int as a result. So we're going kind of first hop and then second hop, and we wind up with the value 42. Here, we are dereferencing Brooklyn once. So we're following the arrow. We get another int, and this int happens to also be 42. And so we're comparing 42 to 42, and we get 1. Okay, so it's, the things to keep in mind here are, number one, keep track of what is a pointer and what is it a pointer to. In other words, at the level of types, for every variable, you should know what type it is. Is it an int? Is it a pointer to an int? Is it a pointer to a pointer to an int? These are all very different types. But then separately from types, you need to keep track of values. So what is the value of every variable? If it is the value of an int, if the variable is type int, the value is just going to be an int. Whereas if the variable is a pointer, the value is going to be one of these little arrows. It is going to be an address in memory of some other variable. And so whenever you see one of these little stars, that means take whatever address is there and go there and look up what is there. And that might be an int. It might, be any other type of variable. And in particular, it might be a pointer. And it's always the type of the variable that lets you keep track of, once you follow this pointer, what type of thing are you going to find there. So I think that's kind of the way to really think about it. Always keep track of what is the type of the variable that you have. When you see a star, you're removing one pointer of from the type. When you see an ampersand, you're adding a pointer to the type. And so always kind of keep track of what is the type of thing that you have, and then independently of that, be keeping track of what is the value of that variable or of that expression. and make sure that the value corresponds to what type you think it is. Okay, so those are these questions. And now we're actually doing an assignment, and we have a bunch more questions. So let's run through these. So here we are saying Adams gets Brooklyn. I like to, in one of my early computer science classes, the instructor started using this terminology gets for the assignment statement. And I find that actually, just calling this gets instead of calling it equals really, reinforces that this is an assignment statement and not an equality. So, you don't have to get into that same type. You don't have to get into that same habit, but sometimes it makes it easier to, not get confused when you're reading code. So Adams gets Brooklyn. So here we had Brooklyn. What is Brooklyn? Brooklyn is a pointer. So we're assigning the value of that pointer to Adams. And let's go back and check the type of Adams. Well, Adams is also a pointer. So the variable Adams is actually allowed to hold the same thing as is currently in the variable Brooklyn. And so this is a valid assignment. So whenever you kind of are writing an assignment or reading through code, the first thing you're looking at is this a valid assignment? Do the things on the left and the right have the same type, or at least compatible types, where you can, the compiler can convert whatever's on the right to whatever's on the left. So here we are assigning a pointer to another variable that is capable of holding a pointer. That's totally fine. So now we have rewired Adams to point to the same thing that Brooklyn is pointing to. In other words, the address in memory at that variable Adams is now the same as the address in memory of Brooklyn. Okay, so now this changes some of our equality comparisons. So before we asked, is Adams the same as Brooklyn? Well, no, because they were pointer variables that were pointing to different locations in memory. Now we have done this assignment, and now they're pointing to the same location in memory, and so they now are equal. And of course, because the pointers are pointing to the same thing, when we dereference the pointers, we had better get the same result. And so when we dereference both of those pointers, compare the ints that we get the same int, namely 42, and 42 equals 42. So that's why we still get a 1 here. Now we can ask, what about these meta things? So remember that meta was pointing to Adams. We haven't reassigned it. It is still pointing to Adams. So when we compare meta to the address of Adams, we still get true. When we compare meta to the address of Brooklyn, well, meta is pointing to Adams. It isn't pointing to Brooklyn. We still get false, namely 0 here. Now, when we dereference meta, that is, we follow this arrow, we look up whatever is there, and that's an address in memory. It's the address of Jackie, because that's where Brooklyn used to point it to, and we assigned that address to the variable Adams. So star meta, we go over here, we look up what is that address in memory. And we ask, is it the same as Adams? Well, meta was pointing to Adams, so when we dereference meta, we get the same thing as Adams. So that's true again. We ask now, is star meta the same as Brooklyn? Remember, Brooklyn is the pointer. It is the address in memory of Jackie. But we assigned Adams to have that same address. So these two values in memory, the values of these two pointers are now the same. And so star meta, namely Adams, is the same pointer, is that same address in memory as Brooklyn, because we did this earlier assignment. And that's why we now get a true right here. And of course, the double dereference, namely following both pointers, looking up the int there, we still get 42 here, we still get 42 there. Those two still compare as equal. Okay, so what other questions do you have on these two examples?
I don't know when if you would ever need to do it, but if you were doing like a pointer to meta, would you just add an additional asterisk to it, or would it just be like, is the max 2 a pointer to a pointer?
Absolutely, you just add another asterisk. In C, you keep track of all of the different fine-grained distinctions between pointer to pointer, pointer to pointer to pointer, pointer to pointer to pointer to pointers, you know, as deep as you really want, or at least as deep as you can without, you know, overflowing your compiler's memory or something like that. So C absolutely does keep track of all of those types, even incredibly complicated types and incredibly nested types. And whenever you add another asterisk when you're declaring it, you know, you're just adding another pointer to the definition of the type. And as you know, dereference pointers, as you take the addresses of things, C absolutely keeps track of how many levels of pointer to you have on that variable. And, you know, in particular, it won't let you do things like, you know, say you wanted to write Adams gets meta. The C compiler wouldn't let you do that. It would give you a type error. It would say those two things are different types, even though they are both pointers. But they're pointers to different things. And there is a distinction in C of, you know, what it is that you're pointing to. Two pointers that point to two different types of things are considered themselves different types of pointers. Okay, so that's a really important distinction to keep in mind.
So to follow up on that, if you're writing a pointer to another pointer, you have to know how nested that pointer is, right? You can't just write a general pointer to any level of pointer.
At this level of things, yes, that is correct. Later on, we will talk about kind of more generic pointers. It turns out you can write a type called void star, which is a more generic type of pointer. But you have to be, you know, at that point, you're telling the compiler, all of this wonderful work that you're doing to keep me from shooting myself in the foot, I don't want you to do that. I am going to explicitly take responsibility for keeping track of all of these types, and when I break things, I'm going to keep both pieces. So, you know, yes, later on we will see, you know, how to do various exceptions. Of course, you can still write a cast where you can convert from one pointer type to another. But remember that whenever you're doing that, you're basically throwing away all of the compiler's good intentions in trying to keep you safe as C can help you, which, as we've seen, isn't quite as safe as like Java will try to keep you. So yes, later on we may see exceptions to this, but for now, I really want you to think of, you know, when you write a pointer, you in your mind should know what type of thing it is pointing to, and you need to declare it correctly. Okay.
Thank you.
Mm-hmm. All right, more questions. I see in the chat, For the record, Brooklyn, Hitchhiker's reference, yes, absolutely, 42, the ultimate answer to the ultimate question of life, the universe, and everything. If you haven't read it, go find a book. Can you please go over the output of the code on page 22? So let's go to page 22. All right, so hopefully this is the one, and hopefully everybody can see it. So let's go through what we are doing here. So here we have a string variable. It's a variable called string, but it is also a string in C, which means that it is an array of chars. So an array of chars where we have the individual characters that are in the string followed by the null character. So there are two equivalent ways of declaring it. Here we are explicitly assigning individual characters to individual locations in the array. Notice the difference here between just a raw 0, meaning the integer 0, which gets converted to the char null, as compared to 0 in single quotes, and as compared to \0 in single quotes. So \0 in single quotes would be the same thing as this, whereas 0 in single quotes would be the digit 0, which is quite different from the null. So that's one syntax. Here is a different syntax, the double quote syntax, which, remember, basically implicitly puts a null at the end of all of the characters that you do see. So these two declarations are doing the same thing. Here we are declaring a pointer variable, PC, pointer to char. So it is of type pointer to char. So the only things it can point to, unless you do, unless you break the compiler by putting in casts, the only things it can point to are chars, not pointers to chars, just chars. So here we are initializing this variable PC to point to whatever string was plus 1. So what is string? Well, we know that string is the name of this array of chars. And so here in this expression, we are utilizing the fact that the name of an array can be treated as a pointer to the first element of that array. Okay, so if we just wrote char star PC gets string, then PC would be a pointer containing the address of the first character in the array string. In other words, it would be pointing to the beginning of that array. Here, we write string plus 1, which means that PC is now pointing to the next element in the array, the second element in the array, or if you are counting from 0, as we do, it is element number 1 in the array. So PC is pointing to this E. So now, let's figure out what these printfs are doing. We are printing something that consists of the character capital Y followed by a string, followed by a space. So here, this %s basically tells printf, look at your first argument. That argument, I'm telling you, is going to be a pointer to char. I want you to treat it as a string. That is, go wherever this argument points and start walking until you get to the end of the string. And how do we know we've gotten to the end of a string in C? Well, we encounter a null. So here, let's look at this big, complicated, expression. How do we interpret this expression? Well, we have to figure out which thing we're doing first. Are we doing this address first, or are we doing this array dereference first? So we need to go to our handy dandy table of operations in C, and we need to figure out which has higher precedence. That is this square bracket dereferencing of an array, does that bind tighter? Does that, does it have higher priority than this ampersand, which is taking the address of? And the answer is yes. So when you have both this ampersand and this expression in square brackets, we know by consulting our table of precedence that we have to evaluate this thing first. So the very first thing we're going to do is figure out what this means. So this is taking the element number 1 of the variable string. So treating string as an array and figuring out what element 1 of that array is. And because we're counting from 0, as we always do, this is element 0 of the array, this is element 1 of the array. So if we just had this little piece, what we would have is just the character E. But now we need to do the rest of the expression, namely this ampersand. So now we need to take the address of, the second element, element number 1 of the array named string. And so this entire expression is basically going to be the address of this char E in this array. And that's what gets passed to printf. So now printf, it doesn't care what complicated thing you put in there as its first argument. All it knows is, I see a %s, I am getting a pointer to a char, and I'm going to start following the pointer and start walking forward in memory, reading chars, writing out chars until I get a null. So what is the output of this printf? Well, we're going to print the y, because that's just a constant thing that we print in the printf format. And then we're going to print this e, and then we're going to print this L, then we're going to print this L, then we're going to print this O, and then we're going to stop printing. And then we're going to print this space. So the output of this first printf statement is yellow, Y-E-L-L-O, followed by a space. And now the second printf, hopefully that starts making a lot more sense. Because again, printf doesn't care, what complicated thing is there. In this case, it's a particularly simple thing, simple expression that it's getting. It doesn't care. Printf is just going to start, hey, that's a pointer to chars. I'm going to go there and I'm going to start printing out characters. Here, PC was also pointing to this lowercase e. And so this printf is going to print out a J, E, L, L, O, and then it's going to stop printing this string, and it's going to print out the exclamation point. So you get yellow jello.
I have a question. Why is string 1 in the first printf statement getting the character E and not the address?
Okay, this is how the square brackets work. The square brackets actually do 2 different things. The square brackets first take whatever offset you have here, and they walk that many elements into the array. Or you can think of it as they add this number of elements to this pointer. So that's step one. Step two is they follow the resulting pointer. Okay, so this syntax, always think of this as doing two different operations. One is you're manipulating some pointer by adding an offset to it. And the second step is you're following that pointer. And if you think of this as, what do you typically want to do with an array? You want to look up an element in the array. So imagine this wasn't a string or anything like that. This was, an array of ints. What do you usually want to do? Well, you want to look up element 42 in the array. So the name of the array is the same as the pointer to its beginning. And so in order to look up element 42, you have to change that pointer to point 42 elements later, and then you have to follow that and look up what's there. So that's kind of why we need this extra ampersand here, because we want to go from what is in element 1 of this array back to the address of element 1 in the array. Imagine that here we didn't want to use this extra ampersand. Imagine that we just wanted to manipulate that string pointer. So how do you think we would have done that? So can we get the effect of this expression without writing an ampersand? How do you think you would do that? In fact, there's a version of this on the slide already.
You do string plus one?
String plus one, absolutely. Right, so this is the important distinction between an expression like string plus one, which basically just takes this pointer and manipulates the pointer, it takes an offset from that pointer, and this dereference expression. This literally is string plus one and then dereference that pointer. Go to where that resulting pointer is pointing. And because we've done that dereference, to convert it back to a pointer, we need to take its address.
Okay, that makes sense. Thank you.
Okay. More questions?
In lecture, you also mentioned that you should make all of your strings the proper size. Does the null character count as part of that size, or?
It's taking up memory. It had better count as this is one of the common memory management errors that we see, is that students declare a array of char and they studiously count up how many characters they need. They forget the null, and suddenly you have an array that is too small to hold what you need it to hold. And so you put something in there and it actually runs off the end. And what happens when it runs off the end? Well, it writes to some other piece of memory, and probably there's something important in that other piece of memory, like another variable. This, in fact, is the entire premise for your last assignment, is what happens when you start writing off the end of the memory you have allocated to hold particular variables. So yes, count your nulls. More questions? I saw that there was a question in the chat that Christopher answered about, doing multiple pointer declarations per line. And the point is that when you're declaring multiple pointer variables per line, you really want to group that asterisk together with the name of that variable, because you need to have the asterisk before every single pointer variable that you're declaring on that same line. And so you will find multiple styles in use. A lot of people, even if they're declaring one pointer variable, will go ahead and group that asterisk with the name of the variable, just so they don't, just so they train their fingers and they don't get into this problem where you write char star I comma j, and now I is a pointer to char, but j is just a char. So this is definitely something to keep in mind, and it is one of the interesting little wrinkles of C, where these days the way we tend to think of typed languages is that the pointer really is part of the type, whereas back when they were designing the C language, they wanted to emphasize kind of the syntax of declare it like you would use it. So char star I means that star I is a char. Therefore, I must be a pointer to a char. Just different design decisions that were made in the design of the syntax of the language. All right, more questions?
I had a question. When we were talking about in a lecture arrays with functions, we mentioned to be careful not to return an address from the function stack. And I guess I understand why that's important, but could you maybe give an example of where you might accidentally make that mistake and how you could go about avoiding it?
Sure. So a common situation might be, you're passing in an array into a function, and now you want to return the address of an element in the array in the function, from the function. So, okay, that's fine. That's allowed. And now, 2 months later, you're hacking on that function and you say, shoot, I really need to manipulate this value, but I don't want to manipulate the original array. I know, I'll create a brand new variable in my function. I will return the address of that variable because the function already needs to return an address. And there's where you run into problems. So in general, when you're returning a pointer from a function, always treat that as guilty until proven innocent. So always, be very careful of what exactly are you pointing to, because if it's something you created on the fly in the function, you're not allowed to return a pointer to it, because that's going away as soon as the function invocation goes away. So, like I said, be suspicious whenever you're returning a pointer from a function. A lot of times it's just fine. A lot of times what you're doing is you're manipulating something in an array, but now you're returning the address of an array again for convenience or things like that. But every single time you do that, it's worth another look, because this is one of the things that can really bite you. Yeah.
Thank you.
I had a quick question just to clarify on that.
Mm-hmm.
So given that rule, if we say wanted to return an array from a function, excuse me, my phone's going off. There we go. So if we wanted to return an array from a function, we would have to declare that array outside of the function and then pass it back into the function, then return it back out. Couldn't would we not be able to create
so you can create an array. It depends on how you do it.
Okay.
So if you write inside your function int a bracket 10, where you are creating a variable that is itself an array, and you're just trying to declare that in the function, that's the one where you run into problems. If you actually want to create an array within a function, you have to ask the system to give you a brand new piece of memory using the function malloc, and now you can return that from the array.
Okay. So if we wanted to create an array inside of if we wanted to return an array from a function, we would have to use malloc so that it isn't overwritten when we exit the function.
Exactly.
Okay.
So the one where you get into trouble is if you don't use malloc and you're just writing down an array, you're just declaring an array from within the function.
Okay.
And it's interesting to think about this as one of the big differences between C and Java. So in Java, you would be perfectly fine creating an array inside a function or a method, and returning, somehow doing manipulations where you are returning, references and stuff like that. And the reason you can get away with doing that in Java, Java doesn't have pointers, but it does have these things called references. And references effectively are like pointers. They're kind of followed automatically, but they sort of act a little bit like pointers. And so in order to make this work in Java, what the system has to do is it has to keep track of all of these references, which are really pointers, and where they're pointing. And periodically, it has to kind of go through that entire list of pointers, figure out what everything is pointing to, make sure it doesn't, throw away or reuse any of that memory, and anything that isn't pointed to now is a candidate for reuse. So this is called a garbage collection process. So this is something that is an additional process that is running behind your back. It is running at the same time as your main Java program is running, in order to keep track of memory. In C, we don't have that. In C, you as the programmer are expected to keep track of which memory am I using, am I playing by the rules of when memory is going to get reused, and am I keeping track of basically not doing anything illegal, like returning a pointer to memory that is going to get reused because it was local memory belonging to a function whose invocation has ended.
Okay, that makes sense. Thank you.
So just to add on, a lot of students find it frustrating that we harp on in Precept, what section of memory is this in? But this is exactly the reason. If you have a local variable, even an array, that is stack resident. It is in the function's call stack, stack frame rather, sorry. And so when the stack frame goes away, goes off the call stack, then it's no longer active. Contrast this with, as Professor Rishenko said, malloc that says, go out to the heap and get memory. Well, that's not on the stack. That's a different area of memory that we'll talk about soon.
Okay. Thank you.
Yeah. More questions? All right, let's see, were there additional questions in Ed? So there was a question about an array versus a pointer to its first element. And I do think we went over that, in quite a bit of detail, but just to kind of reinforce that, the name of the array can be treated as a pointer to the first element of the array. So that's kind of this duality that we're playing with in Let's see. Spaces, tabs, assignment submission. I think most of the rest of these have been answered. All right, last call. Going once, going twice. All right, thank you everyone for showing up, and see you next Monday. Have a great rest of the week and a great weekend, everyone.
Thank you.